we did the proof of number 2. I'm erasing it right now. But the proof of number 1, it's almost the same thing I just did. When you take the divergence of the curl, you get a contraction. It's again going to be this like flipping one pair of indices, but then flipping the pair of indices in the epsilon ijk, and then that gives us minus what we started. Like the proof is going to be similar to what I did, but all right. So, as I was telling you guys, this is Introduction to Electrodynamics by Griffiths, and basically, Griffiths, listen to me, Stewart, no, wait a minute, yeah, Griffiths. And example 4, I want to share with you what are known as Maxwell's equations. What are Maxwell's equations? They're divergence. The divergence of the electric field is equal to rho over epsilon naught. The curl of the magnetic field is equal to minus, oopsie, oh no, mu naught, oh I'm sorry, I meant to put E there. The curl of the electric field is equal to minus the time rate of change of the magnetic field. The divergence of the magnetic field is equal to 0. The curl of the magnetic field is mu naught times J plus epsilon naught times partial E partial T. These 4 equations are known as Maxwell's equations. The first one, so just a little bit more context here. To be clear, rho is not, for us in here, rho is equal to dq dv. It's the charge density. The charge density. And here J is equal to the current density. It's an area density. So it's not the spherical radius, okay? That would be weird. Do you guys know the names of these? I mean, I don't know why you would, but maybe you had a really good physics teacher in high school or something. The first one is called Gauss's law. This one is Faraday's. This one is no magnetic monopoles. I can't spell. Monopoles. And the last one is Ampere's law. With this right here being Maxwell's correction. So essentially, the study of electromagnetics is the study of the analysis of these 4 equations, how to find their solutions and interpret them. All right. Physics 232 is about this, but it's not quite so on its, like, depending on who your instructor is, you may or may not actually see these equations written in this way. What you'll see is the so-called integral form of these equations more so. All right. Now, okay, let's think about these equations in empty space. In empty space, what do you have? What's the density is 0, right? And the current density is also 0. There's no current or charge in empty space. There's nothing. So what do Maxwell's equations look like in empty space? So this is just equal to 0, right? So in empty space, we just have the divergence of the electric field is 0, the divergence of the magnetic field is 0, the curl of the electric field is equal to mu naught epsilon naught partial B partial T. Oopsie. B. Sorry, I keep flipping these around. All right, the curl of the magnetic field is this, and of course the curl of the electric field is still the same thing as it was. All right. But look at this. There is this handy dandy identity right here. Let's see what that means physically. Yeah? Let's plug Maxwell's equations into part 3 here. What happens? So we have the curl. So let's put I'll put F equals to E to start with. So we've got the curl of E. What was the curl of E? Minus partial B partial T, right? And that's going to be equal to the gradient of the divergence of E, which is kind of boring, but I'll write it down, minus the Laplacian of E, which I'm not going to expand this time. Okay? And, okay, well that gives me partial T of the curl of B, which by the way is minus partial T of minus partial sorry, moment. That gives me mu naught epsilon naught partial E partial T. I'll get out of the way here in a second. Equals to minus nabla squared E. So therefore, let me write in the middle board, you can see better. So what I'm doing right now, guys, is I'm plugging Maxwell's equations into identity 3. So we just found the mu naught and epsilon naught are a constant. So what I've got is like minus mu naught epsilon naught partial squared E partial T squared is equal to minus nabla squared E, right? Because we know the divergence of the electric field is what? It's 0, right? So to clean this up, we have that the Laplacian of the electric field is equal to mu naught epsilon naught partial squared E partial T squared. What do you think is going to happen when we look at the magnetic field? So we've got the curl of the magnetic field is equal to the divergence, the gradient of the divergence of the magnetic field, right? Minus the Laplacian of B. Okay, so the curl of the magnetic field was what? It was minus partial E partial T, right? That was Faraday's law. The divergence is 0, right? So I have this is equal to minus nabla squared B. We can pull the time derivative out. Minus partial T of the curl of E. And that implies what? Well, this gives us that minus partial T of, what was the curl of E was what? It was, oopsie, I forgot something. What did I forget? I'm an idiot. Look, is that right? Guys, come on, don't let me do this. No, this was supposed to be what? Mu naught epsilon. There was no minus there, right? Mu naught epsilon naught, all right. But now we've got the curl of E. So the curl of E is going to give me that minus partial B partial T. So therefore, we get that nabla squared B is also equal to mu naught epsilon naught partial squared E partial T squared. Wait a minute, the electric and magnetic fields, they satisfy the same equation in empty space. All right, so when you take physics 231, perhaps at the end of the course, Professor Dromby might tell you this, partial squared F, partial squared F partial z squared equals to 1 over v squared partial squared f partial t squared. This, what I'm writing right here, this is a wave equation. It's a wave equation for like a transverse wave on a string. That's the equation that a wave on a string has to satisfy. Now it turns out that the velocity of the wave is equal to the square root of the tension divided by the linear mass density of the string. So in comparison, we can see that the electric and magnetic fields, because partial z squared is like the Laplacian in one dimension, okay? So the Laplacian is a three-dimensional generalization of just the second partial derivative. And so we see that those are wave equations. And what's the speed of the wave? If we compare this to my wave equation with one, so like the speed of the wave is equal to mu naught epsilon naught by comparison. So the electric and magnetic fields in empty space satisfy a wave equation. And the speed depends on mu naught and epsilon naught, the permeability and permittivity of free space. And if you calculate that, 1 over the square root of mu naught epsilon naught, guess what that is? This is, in fact, 3 times 10 to the 8th meters per second. Also known as the speed of light. See, this derivation shows that electric and magnetic fields in the vacuum behave as a transverse wave that travels at the speed of light. What that means then, apparently, it would be an incredible coincidence if electric and magnetic fields aren't what form light. This is what Maxwell discovered a little bit after the time of the Civil War. Maxwell discovered this because Maxwell was the guy who added, well, Maxwell's correction term. And if you notice the derivation here, this played a pivotal role in seeing this work out like it did. Now, so last here, and we're done. Something to show you. I want to show you what I didn't do today, because it's quite insidious. So tomorrow, we will start in our study of integral vector calculus. Tomorrow we will be doing the line integral. So the, I actually don't know if I have the number 4. Well, the one I showed you guys in the front of the textbook, I don't think that's in my notes. It's too horrible. I might have it written up in like my electromagnetics notes from this semester. I don't know. Eventually it'll turn on. And then I do have a proof of the identity 3 we're just using. It requires a deeper magic to prove it. You need to know something. So when you calculate the curl of the curl, you end up with this contraction of the epsilon symbols. And it turns out that there's an identity that you can trade the contraction of 2 epsilon symbols for a difference of these Kronecker deltas, which then gives you the 2 terms, which gives you the formula. But like, if you were to derive this without the summation notation, it'd be a couple pages. Pretty sure. Anyway, is this on the test? Well, no, obviously not. Anyway, thanks guys.